Alright, so another approach for this problem that we solved is basically minimum cost to make at least one valid path in the grid is 0, 1 BFS. So the intuition is that Dijkstra's algorithm works well for finding the shortest path, but a problem has a unique feature that the path costs are either 0 or 1. This is key because any path with only 0 cost edges, no matter how long, will always be better than one that uses even a single 1 cost edge. Therefore, it makes sense to prioritize exploring the 0 cost edges first. Only after the 0 cost edges have been explored, then we should move to the 1 cost edges. And this insight basically leads us to the modification of BFS algorithm, that is 0, 1 BFS. So traditionally, what we used to do in BFS is that we use a normal queue, right? But in 0, 1 BFS, we adjust the traditional BFS by using a DQ, that is double entry queue, instead of a regular queue. Now the DQ allows us to prioritize 0 cost edges more efficiently. Each element of the DQ allows us to basically store the row and column indices of a cell, and we'll maintain a minimum cost grid to track the minimum cost of each cell, minimum cost to reach each cell. So as we visit each cell, we will evaluate all the 4 neighboring cells, that is 4 directions. If moving to a neighbor doesn't require a sign change, that is the move is a 0 cost change, we add that neighbor to the front of the DQ because we want to explore it immediately. Otherwise, we see if there is a sign change required, that means it is a 1 cost move. Then we add the neighbor to the back of the deck, not DQ but deck, ensuring it gets explored later after all the 0 cost moves. So for each neighbor we explore, we calculate the cost to reach it and compare it to the current value in the minimum cost grid. If the calculated cost is lower, we update min cost with a new cheaper value. Once the BFS completes and all cells have been processed, the minimum cost to reach the bottom right corner will be stored in minimum cost, and we return this value as a solution to the problem. The below slideshow demonstrates the algorithm in action, so you can go through this. Basically, in this one, let me show you. We have a deck. Since we are starting at cell 0, 0, we add 0, 0 to the front of the deck, right? So this is basically the matrix that we have, and we have initialized 0. All the other cells min cost in the min cost grid, that is this one. In the min cost grid, we have all the other cells initialized as int max, and min cost of 0, 0 grid is 0, right? So this is the deck, and in the next one, we basically traverse 0. This basically the arrow. As you can see, the arrow towards the right was already towards the right, right? So we don't need to change anything. But this one we have changed. Let me go back to the previous slide. So to show you, basically our we check neighbors, we check them, and we see 0. This one will be 0 since there is a 0 cost, and 1, so we have added these. Then we move on. We check again that for this particular arrow, the neighbors are this and this. So since we are heading in the same direction, the cost will be 0, but here the direction changes, so we have added the cost 1. Therefore the cell 1, 1 is added to the back, and the cell 0, 2 has been added to the front of the deck, right? In the next one, we see that the only neighbor of this one, that is the 0, 2 cell, which will now be popped. So that has 0, 2 cell has been popped, you see, and the neighbor is facing now it is facing towards the down. My value would be marked as 1. Similarly here, for this neighbor, you see the previous one, that is this cell, has been popped out, and we visit this. We check the neighbors and fill min cost array in the same way, and we keep on updating till we reach the final value. So now we have reached destination, and we see that we have stored the minimum cost in all of these. So 1 is the minimum cost, so we needed 1 modification. Now going over the algorithm for more clarity. So this is the editorial, you can go over it, go through it. So first we initialize the 2D array directions with 4 direction vectors representing right, left, down, and up movements. So this I have already done. Here you can see directions I mentioned here, right? So for the 4 directions we have done this. Now we have the min cost function. So we initialize variables num rows and num columns, which I've set as m and n, which is the number of rows, and n is the number of columns. Then we create 2D array min cost, which I've already done, this one, and initialize it with infinity to basically we are tracking the minimum cost to each cell. Then we are going to initialize all cells in the min cost array to the maximum possible integer value, that is int max. Now the changes are occurring. So we create a double-ended queue deck for 0, 1 BFS implementation, and we add the starting position 0, 0 to the front of the deck. Then we set the value of minimum cost 0, 0 to 0. This we have done here, right? Since it's the starting position, then we enter a loop that continues while the deck is not empty. Extract the current cell from the front of the deck. For each of the 4 possible directions, calculate new position by adding direction vectors. Then we calculate cost. Set cost to 0 if the current cell naturally points to this direction. Otherwise, set cost to 1 if we need to change the direction. So you can see this check here is going to be applied again. So that's the same logic. If the new position is valid, the new path is cheaper, update the minimum cost as we have done here, and push it to the. Now we're not going to be requiring this, so priority queue is not required since we are using a deck data structure. So if the cost is 1, add the new position to the back of the deck, and if the cost is 0, add the new position to the front of the deck as I had shown you in the visualization. And finally return the value of minimum cost n-1, n-1, which represents the minimum cost to reach the bottom right or the target cell. Then helper method, if is valid, basically is to check for a cell to be in bounds. That's it. So now we're going to be coding that part up. So let me show you exactly how to code this. So basically the things that are going to change, I'll show you. This directions would stay the same. Till here we have the same code. Now here is the change coming. So basically we need to remove this since we are not going to be using a priority queue. So we're basically going to use a deck, right? Let me just make this clear. So a deck would be used. So deck of pair of int comma int, right? Pair of int comma int. Uh, let us name it as deck itself, and we push in the deck dot push front to the front. We are pushing our starting position, that is 0 comma 0, and we're also setting the minimum cost as at the starting position to be 0. Now we are going to be applying 0 1 BFS. So as I was saying, we now apply 0 1 BFS. So first what we do is that we add 0 cost moves to the front of deck, and cost equal to 1 to the back, right? So all this part will change, the priority queue part. So we say while the deck is not empty. Okay, so just a second. So while the deck is not empty, we're going to get the basically the row and column initially, row and column. So if you're getting confused with all of this, let me just remove this, right? So as to make it clear. So while while the DQ is not empty, we basically get the front value and then we pop it from the front. DQ dot pop front, that's the function for this. Now we try the 4 directions. So we go over all the 4 directions. So for int direction is equal to 0, dir less than 4, and dir plus plus. So int n, the next x coordinate is going to be row comma column. Let me just write it for simplicity. Let me say x and y. So nx is equal to x plus d of 0, and sorry, directions of dir of 0, right? And similarly we have the ny coordinate, and this would be ny, right? So now we calculate the cost, that is grid of nx comma, sorry, grid of x comma y, that is the previous one, is not equal to, again, as I had said, that since direction here dir is ranging from 0 to 4, 0 to 3. So in the question given, the values in the grid are from 1 to 4, but direction here is from 0 to 3. That is why we add plus 1 to get all the values in between 1 to 4, right? So 1 2 3 4 to get these values. So what this means is that if the cost of the grid value is not matching with the direction of the arrow, right? If that is not matching, then we have an added cost of 1. Then we have added cost of 1. Otherwise we have cost of 0, right? Now we check if the position is valid and it's a better path. It's a better path. If is valid, let me write valid nx comma ny and m and n. If it is valid and the minimum cost of nx and y plus the cost value is less than the minimum cost of the new one. Okay, so it's nx and y. This one should be the previous one. This is x and y. So if the previous one plus the cost is less than that, then we update this value, that is the new value, to be equal to the previous grid value, previous min cost grid value plus the cost. And in case the cost is equal to 1, then we add 2 back. So in case cost equal to 1, so if cost equal to 1, then we add to the back, that is dq dot push towards the back the new row and the new column. Otherwise we push towards the front, else to front. So that is by dq dot push front nx and y, right? And finally we have to similarly just return minimum cost m minus 1, n minus 1, and that's it about the solution using deck, which uses 0 1 BFS. And yeah, as you can see, it has also been accepted. So yeah, that's it about the problem, and thank you guys for watching.